So there's our question up at the top. Are problems in P strictly easier than the hardest problems in NP? So to answer a question, or to even have language to discuss this question, we need to have some notion of what it means for one problem to be harder than another. So our sub-question now is, what does it mean to say P, let's do this. What does it mean to say that problem P2 or prob 2 is harder than P1 or problem P1 or prob 1, we'll just call it that. Right? What is the right notion of kind of computational challenge here in this thing? And here's the thing that we would like hardness to describe. We would like to be able to say that when problem 2 is harder than problem 1, this means that if problem 2 is tractable, then problem 1 is tractable. Okay, so here's the kind of notion of hardness that we're gonna, or notion of relative hardness that we're gonna carry through the rest of this lecture. So suppose that problem P2 is harder than problem P1, right? So suppose this is the case. Oops. Suppose that P2 is harder than P1. Okay, so we've got this kind of this hypothesis. So what do we want that to mean? Well, we want this to mean that if P2 can be solved fast, then P1 can be solved fast. Okay, we want this to mean that in some sense, in a strong sense, we want this to mean that an algorithm that solves this problem can also solve this problem. Okay, we want this to mean that if problem 2 is, let's just say, is tractable, then problem 1 is also tractable. Okay, so this is a slightly weird notion of thinking about relative challenge in computation, but it turns out to be a really useful one. And now let me show you kind of the device, the mathematical device that we use to argue about this concept right here. But as I'm going through this, keep in mind that whenever I say problem 2 is harder than problem 1, what I mean by this is an implication, right? I mean that, problem 2 being harder than problem 1 is defined to mean, in this lecture, is defined to mean that if problem 1 is actually easy, then so is, or if problem 2 is actually easy, then problem 1 is as well. Okay, so that's what it means to be to have this relative challenge between problems. And we're going to work on we're going to develop some tools here and work on some intuition. So you're not going to just be left with this, because I recognize that this is kind of a strange way of thinking about it. But let me now provide you with some stuff. So the formal kind of device we're going to use for this, we're going to use to argue about this, is something called a problem reduction. So formal device is the idea of problem reduction. All right, so let's imagine that I have a circle here that represents the set of all instances of problem 1. So all instances of problem 1. Okay, so problem 1 is a decision problem, right? We're living in this world where there is where every problem we're talking about is a decision problem. So some of these instances have a yes answer, and some of these instances have a no answer. So let me just represent that like this. So here's the yes instances. Here are the no instances. So there's our no instances. Okay, and so if you're thinking about this as that array search problem, all of the arrays, all of the pairings between arrays and thresholds such that there exists something in the array that's larger than the threshold. All of those instances, every single pairing of those two lives up here in the yes instances, and every single pairing where there is nothing in the array that's larger than the threshold exists in the no section of this set. Okay, and so there are infinitely many problems in both of these. For any non-trivial problem, we'll have these are both going to be massive sets with infinitely many things. So there's our grouping for problem 1. So now we'll do the same thing for problem 2. So here's all instances of problem 2. And we'll actually do one of these in a second here with some examples. So here's all instances of problem 2, where we have, again, we'll group them with the yes instance. Yes instances here, and the no instances here. So a problem reduction is a function which converts instances of this problem into instances of this problem. Okay, so here's our definition. The first piece of the definition. Okay, a problem reduction is a function, and I'll call it t. And so you could also think of this as an algorithm, right? That it likely will be more sensible for you to think of this as an algorithm. So it's a function t that converts instances of problem P1 into instances of problem P2 in the following way. So it converts yes instances of problem P1 into yes instances of problem P2. Okay, so there's this machinery here in the middle, t, and what t does is it takes everything over here and it maps it somewhere over here, right? I don't care where it maps it over here as long as it ends up in the yes category, and it takes no instances of problem P1 and maps them to no instances of problem P2. Okay, so it converts, let's just say, yes instances, yes of problem 1 to yes of prob 2, and no of problem 1 to no of problem 2. Okay. So why would we do this? What's the purpose of such a device? Okay, well now suppose let's just, for instance, let's just say suppose I have a problem reduction that I can compute fast. So for all of the following lectures, let's just have this running assumption that if I'm talking about a problem reduction, then I mean that it is a polynomially computable problem reduction, right? It's an algorithm that runs in polynomial time. And this algorithm, it doesn't solve either of these problems. It just converts this problem into this problem. It just, if you want, it rephrases the question that we're asking here into a question that is in the language of over here, right? All it does is translate from one problem domain to another problem domain. But let's suppose we have a guarantee that that translation is fast. Okay, so we'll just take this running assumption that t is a polynomial time algorithm. Now, suppose I have this problem reduction, right? This polynomial time problem reduction that converts this problem into this problem. And suppose second that I have a polynomial time algorithm that solves this problem. Okay, so now let's take another assumption here. Let's suppose that I have an algorithm. Let's call it A2. The 2 corresponds to problem 2. A2 is a polynomial time algorithm that solves problem P2. That solves P2, or problem 2. Okay, so what can I do with these two things? Well, I can use my problem reduction and my algorithm for problem 2 to solve problem P1. Okay, then here is my claim. My claim is that A2 of t of x, okay, where x, we can think of x as an instance of problem P2 or problem P1, make sure that's showing up there, that this is an algorithm for problem 1. And moreover, it's a polynomial time algorithm for P1. Is a polytime algorithm for problem 1. Right? Where, to be clear, this x is meant to represent an instance or a set of inputs for problem P1. Okay, so here x represents an instance of problem 1. Okay, so if I have some knowledge about these problems, so some knowledge about the relationships between these problems first, where the relationship between these problems comes in the form of this problem reduction, T, where T says I'm an algorithm that can rephrase questions that I'm asking here into questions that I'm asking here. And then moreover, I have an algorithm for identifying what the answer is to a question here. If both of those things, if the problem reduction is polynomial time and the algorithm for problem 2 is polynomial time, then I can use them together to solve instances of problem 1. Right? I can first, if I have an instance of problem 1 that I want to solve, how do I solve it using these two pieces? Well, first I use my function t to convert it into an instance of problem 2. Then I use my algorithm for problem 2 to solve it, right? Identify whether or not it's a yes or a no, right? I know that, if I have an algorithm that solves problem P2, then it takes a yes instance and returns yes, and a no instance and returns no. And because of the form of my problem reduction, I have this guarantee that the answers will be consistent in these two problem classes. So that means I can just return the answer that I got for problem P2 as an answer for problem P1, and I'm done. Okay. So what does this mean? Well, this means that if I have these two facts, so let me do this. So T now maps problem 1 to problem 2, and I have a polynomial time algorithm for problem P2. So what does this mean? I mean, this means that that problem 2 is in the class P. So prob 2 is in the class P, right? It has a polynomial time algorithm. Then what do I have? Well, then these two things put together give me this, that there is a polynomial time algorithm for problem P1, and I can rephrase that as saying problem 1 is in P. Okay. So if I have, so here's kind of the full statement. Okay. Oops, let me do this. So if I have a polynomial time reduction from P1 to P2, okay, so if a polynomial, let me do this. If prob 1 is polynomially reducible, to problem 2, then I have the following. Then problem 2 being in P implies that problem 1 is in P. Okay, so memorize this. Okay, this is a critically important fact. Memorize the direction of the implication here, right? So what this is saying is that if there's a fast way of converting this problem into this problem, then this problem can't be any harder than, or this problem can't be any easier than this problem. Okay? That if this problem has fast algorithms, then those fast algorithms can be used as fast algorithms for this problem. Okay? And so this is kind of the crux, this polynomial reduction concept is the crux of how we define NP complete and then how we talk about the P versus NP problem.